To start a discussion of the gas giants, we need to talk about Jupiter. And such an amazing picture here. This is Voyager 1 as it was approaching the planet, going from about 58 million kilometers away to roughly 31 million kilometers away. There was a span over a couple of hours, and so as it zoomed up, you could see these rapid waves, these rapid storms rotating around on the planets. So, some facts about Jupiter. It's about 5 astronomical units away from the sun, and it has this rapid rotation of 9.9 hours. Once around Jupiter is only 10 hours. A year on Jupiter, how long it takes Jupiter to go around the sun, the sidereal period, is about 12 years. And yes, the giant planets are giant for some obvious reasons. Their masses and their radii are huge, Jupiter being more than 300 times the mass of Earth, 11 times the radius. But look at the density, right? Jupiter, in terms of, say, water, the density of water is about 1 gram per cubic centimeter. So Jupiter's not a very dense planet. It's just this combination of, yes, it's very massive, but it's also so huge it makes it a very low density object. Last thing we'll discuss here is its tilt. Remember, this is the tilt towards the sun, Earth nominally being about 23 to 24 degrees tilted. Well, Jupiter has a very small tilt, only about 3 degree tilt. So in terms of the seasons on the planet, Jupiter's seasons will be pretty mild. Well, mild when you talk about storms on a gigantic planet. With every one of the giant planets in our solar system, I want to just briefly mention just the number of spacecraft or objects that have flown by or visited them. Notice that we're talking about the types of missions here. When we mean by flyby, we mean that Pioneer 10, Voyager 2, all these, their destination wasn't Jupiter, they were flying by them. In fact, Ulysses was doing a gravity assist. It basically entered in a relatively close orbit to Jupiter and stole some momentum, gained some kinetic energy to boost itself further out into the cosmos. Well, Galileo, that was an orbiter that was meant to go there. And I'll make my discussion now on Juno, the most recent one. So as a quick reference, here's Jupiter and its 4 Galilean moons, Io, Europa, Ganymede, and Callisto. The Juno spacecraft, it was sent to study Jupiter, its atmosphere, all its wonderful properties. It was launched in 2011 and didn't get there until 2016. Just a reminder, guys, our solar system is huge. When Juno's mission is done, it will eventually run out of, not energy. It'll have plenty of energy due to the solar panels on it, but it'll eventually run out of coolant. The electronics running on this spacecraft do heat up. Think about how warm your computer or phone gets if you watch too many videos. Heck, maybe even this lecture. So that heat, that needs to be cooled off, and eventually the spacecraft will run out. Now, the planned mission, what's going to happen? We don't just let our spacecraft die. We're going to use every last minute of its life to get useful information out of it. So when we do eventually reach the end of Juno's operational life, we're going to intentionally crash it into Jupiter. Now, obviously, there's no surface to crash into, but as that craft plummets through the dense, thick atmospheres, it's going to be taking as many pictures and as much information data that it can gather and transmitting them to us until it finally ceases to function. Because we believe in trying to get as much information out of this as possible. Now, with all that said, I have to share just one great story about naming conventions. And we're going to need a little bit about mythology here. So, how much do you know about Roman mythology? Right? So in Roman mythology, Jupiter is a Roman god. If you want the equivalent in sort of Greek terms, it would be Zeus. And in mythology, Zeus, or the Roman god, what were they very famous for? Having lots and lots of lovers. Anything that basically was alive was a prime target for these gods to approach. So Coming back around, who is Juno in this great dance of mythology? Yeah, Juno was Jupiter's wife. So we sent Juno to go spy on Jupiter. Sometimes astronomers, physicists, we can come up with some very lame names for objects. Other times, we can just perfectly nail and get these absolutely hilarious moments, in my opinion. Looking at this is a slightly enhanced version of images of Jupiter. We see these strong banding patterns here. And you'll have some dark bands followed by light bands and this crazy intricate layers of colors. And what we can say is that the colors are indicative of a complex chemistry. Up here in these upper layers of the atmosphere, as those colors shift and change, we're talking about chemical reactions, this kind of shifting between what's out there, what kind of chemicals are in a higher dominance. And it's constantly shifting because of just the sheer number of storms happening in this atmosphere. Now, the last little comment, I'll ask you guys, does anyone see the dolphin cloud in the picture? Nothing particularly important about it, just, the funny quirk of when we snap the picture and our human brains trying to interpret things in the clouds. Last thing we'll talk about in detail on Jupiter is that magnificent great red spot. And this has been a long-lasting storm. We've been taking pictures of this thing for decades at this point now. And if we believe some accounts, this one isn't verified. This was one astronomer in 1665, and his notes make reference to this kind of blobbish red-orange tint on the planet Jupiter, but no one else really was able to verify, and the astronomer never really talked about it again. But if we take this account as proof, as if we take this as evidence of a ancient witness, the red spot, then we can say this gigantic storm has been raging for at least 350 years. Now, the size of the storm, put this in perspective, here it is in this image. This is Earth to scale. The size of this storm is about the diameter of Earth. And so you have this constantly raging pool, this giant hurricane, and we've seen that the colors of it will change over the years. So some ideas we have about there is that there are a bunch of organic molecules and some red phosphorus or sulfur compounds, but there isn't really a consensus on what is the dominant chemical, what's the dominant chemical reaction happening on the planet. So with that, we'll start moving our discussion on towards Saturn. When it comes to Saturn, some basic principles we can talk about. It's about 9.5 astronomical units away from the Sun. We've talked about this many times before, but remember that its sidereal period, the time it takes Saturn to go once around, is about 30 years. And I'll point this out. This is not a typo, just a funny quirk. The mass of Saturn is about 95 Earth masses, and its diameter is about 9.5 Earth radii. But, just like we talked about in Jupiter, it's a very low density planet. 0.69 grams per cubic centimeter. Reference, remember, water is 1 gram per cubic centimeter. Now, wrapping things up here, the rotational period of Saturn is about 10 hours. So this entire planet, that's almost 10 times the size of the Earth, will do one loop around in about 10.7 hours. So you have a large sea of gas moving very rapidly. This last one, the 26.7 degree tilt, pretty similar to Earth. So the ranges of seasons on Saturn, how the Saturn summer compares to Saturn winter, will be comparable to how an Earth winter and Earth summer are. And the last comment here, I love this image. This is an image 2 days before the Cassini spacecraft was sent to plunge into Saturn. Remember we talked about before Juno. So here is some of the visitors that have gone to see Saturn. All of them are flybys. You shoot these spacecraft out, and as they're whirling past the cosmos, we've tried to plan the trajectory so we get a chance to get the images of these planets. Cassini, however, was an orbiter, and at the end of its life, it was plunged into the gaseous atmosphere, taking as many pictures, as many samples as it could, as it dove deeper and deeper into the atmosphere until we finally lost contact with it. When we view Saturn from Earth, remember about these problems of this, tilt of 26.7 degrees. So as we orbit around, as Saturn is going throughout its long, almost 30-year orbit around the sun, we'll have these different angular perspectives, these angular shots of how we see Saturn. And throughout that time span of just, say, 4 years, we'll go through pictures where you can just barely see the rings. Then they'll come in a nice full view, and then they'll rotate out again. So we're having this constant, our angular view of the planet Saturn is always on this kind of wobble, where we're almost looking at it straight on its edge to seeing it from a bottom side a little bit. Now, continuing on, we see the kind of bands on Saturn, those type of storms. We'd say that we see this similar band structure as to what's on Jupiter. It's not as pronounced, Jupiter being almost 100 times more massive than Saturn. But regardless, you'll still see violent storms and jet streams that are pretty similar to the kind of streams that you'll see on Earth. Now, for reference, here is a jet stream on Earth that has much more oscillatory behavior. But blow up the size of Earth, shrink that. As you blow this up, the oscillatory, the sinusoidal nature of these jet streams will be flattened out, and you'll have more of that band structure that you see on Saturn. Now, one peculiar uniqueness of a storm that we'll find on Saturn is its phenomenal hexagon. On the northern pole of Saturn, there is literally this hexagon storm. Apparently draw it out here. You can just see the edges of it. And it really is a hexagonal shape on the planet. So it's this weird, crazy storm that has these actual corners to it. Here, let's go ahead and turn on the animation. See that start rotating around. So the storm really has these kind of corner cases, and this might sound like a stupid question, but gases, are they solids or fluids? Yeah, I know, it's a fluid. So the question is how do you make corners with a gas? What's producing? What's the mechanism driving these stable edge cases in this gigantic storm? Here's a polar view of the hexagon from 2013 to 2017. And you'll notice how the colors have changed. And this goes back should remind you of the red giant. There's probably some crazy soup of chemistry that's oscillating around, changing the colors of the storm as it rages on. And this one has been stable from the years that we've seen it, at least a decade or so. Probably much older than that. Now, what creates those distinct bands of the corners of the storm? One idea out there is what's called a gradient, gravitational gradients. The gravitational force up here, this is a higher layer of the storm. And as you fall down towards the planet, think of it as like sliding down a hill. You start going into a deeper and deeper gravitational well. So here, gravity, the gravity of Saturn's mass pulling down, will be greater here than it is up here. And that creates this potential turbulent flow, allowing material to be injected in, creating the corners of the storm.